Okay, hi everybody. My name's Christopher Sawyer. I work with the technology enablement team at OSIsoft, and what my job is I work with Pi developers. Those are developers at our partner sites and at our customer sites. I'm amongst a team of 7 people. We're geographically scattered all over the globe, just about every convenient time zone, and we are part of the developers club at PySquare. So if you go to pysquare.osisoft.com, is usually where you can interact with us. That's my email address. I'm pretty sure after this talk you're going to want to start pounding my inbox, so screenshot that now. I also have business cards that I can give out. So you're probably wondering why we're doing this talk. This is a unique opportunity I got this year at PyWorld. Normally when we do a dev talk, it's a deep dive focused on a product. I'm responsible for developer interactions, and it's a constant fight between me and marketing, because marketing wants to talk about product, and they tell me, Chris, it's got to be a product if you want to talk about it. But with developer technologies, once I've found out doing these talks over the years, once you put code up on the screen, all the sales and marketing people at OSI run away. And so there are tons of code slides on here, so they're pretty much not here and out of the room, so I get to say whatever I want to. This talk is actually an experiment. I want to expose you to something that for most of you in this room is something that you might know a little bit about, or you might have messed around with it a little bit in some of your line of business apps. But it's not a concept that's really understandable to generally everybody, and that's a big problem with concurrent programming. So my goal with this is to make it easier for you to figure out what concurrent programming is and take that back home with you for your line of business applications that you integrate with the Pi server. And hopefully we can learn together to make better software. So I'm going to go into some dreariness first. So when it comes to development across the entire industry, both in corporations and outside, there's a pretty big skills issue that's developed. And we have a lot of people who are just not up to speed with REST, don't know much about concurrency beyond, oh yeah, threads. Okay. And the knowledge pretty much ends there. There's a lot of people in 2019 who are still writing Visual Basic code. And I'm not talking about VB.NET, I'm talking about VB6. We still have a lot of that. We also have a lot of VBA code. Some of you are probably are still maintaining process book displays, and you've got a lot of VBA code in there. And staying in that world has segregated a lot of you guys from multi-programming. And unfortunately, bad news is in most toolkits is doing multi-programming is not a fun, easy thing to do. It's usually some advanced topic. So I mean, if you open up any O'Reilly book on Java or a C# and you start to get into, I need to do, concurrency. I need to be able to do multiple things at once. Usually that's always in the back of the book. And it's something you can learn about later. And as a consequence, we have a large amount of the programming labor pool who just their skills are mediocre at this. So this is what a lot of us code like, including me when I first started. And deep down, I think we're still coding like this. We're intensely focused on a project. We're learning. I mean, I was this kid. I had a Compact Desk Pro instead of an IBM. But microprocessors were new. They were super complicated, but writing the software code was fun. It seemed like you could do anything with it. You just put your mind to it, and then you figure it out on your own, and you produce some pretty useful stuff. And that's why most of you have tons of line of business applications that are, they're suited to what you're doing, and they're very useful, and they're very powerful at what they do. But unfortunately, something's cropped up recently, and it's this. This is what I call the CPU performance wall. If any of you have a 7-year-old laptop, like I do, and you haven't bothered to upgrade it, there's a reason for that. This was an awesome study published by a team of 6 computational scientists, and for fun, they went backwards to the first micro, the Intel 8008, going all the way to the present. And they suspected that there was a trend, and it actually started to bear itself out. Around the mid-2000s, you notice here over in blue, look at single thread performance. That really hasn't done very much since around 2003, 2004. And performance in even the latest processors that have come out, like the Ryzen Threadripper, you're running a single-threaded task inside of it is no better than a CPU that you might have bought a decade ago. Now, there are some other trends. Do you notice something at the bottom? Number of cores has dramatically increased. And Moore's law, which is counting the number of transistors overall, that's a straight line, and that's still shooting the moon as far as performance goes, year over year over year. But you're wondering why a lot of your line of business apps you buy a new $20,000 virtual machine, not a virtual machine, but you buy faster physical hardware, or you bump up your VPS, and you're still not getting good performance out of it. That's probably because you're not taking advantage of where the real performance in CPU chip design has been happening. Now, this chart's kind of old. Of course, we're in 2019 now. So I wonder what the trend looks like. Maybe this wall's ended by now. Oh, nope, it hasn't. It's worse. It's not getting any better. It's kind of scary, to be honest. And one of the things that I've come to realize over the last 6 or 7 years is we can't code like this anymore. We have to think more about what we're doing when we're building applications and when we're doing integrations, and how can we take advantage of the hardware that we're buying and not really using. So what's terrible about this is there's a lot of things the CPU wall is impacting because either concurrency is not being done enough or not at all. We're constantly starved for performance. And we spend a lot of time running to cloud computing, which at an econ level makes great sense. But if you're not doing concurrent programming, what you're basically doing is you're just paying rent to somebody else for performance that you're not actually using, for resources that you're not actually using. And so sometimes some of you might have moved some line of business apps up into the cloud, and you realize they're just as slow or just as bad as they were on-prem, only you can just now manage it better. And it's because you probably have a lot of single-threaded stuff going on deep down inside. So we've depended on chips in the past to just deliver on better and better and better performance, and they are. The problem is that you have to take advantage of it, me as well, because we're not going to see single-threaded performance climb any higher. And it's been many years now that we've been kind of stuck in this pickle. On top of that, any of you use PySDK? Remember that? Okay, well, we still have it. It lives inside of a COM single-threaded apartment. You think you can squeeze any more performance? I mean, it really is only going to run on one core. So do you think you're going to get any more performance out of PySDK? Don't call me asking for PySDK performance boosts. You're not going to get any more. AFSDK is multi-threaded, by the way, so if you haven't made the leap to or the transition from PySDK to AFSDK, now's a good time. So concurrency. Concurrency 101. Concurrency is the habit of being efficient at multitasking. My boss, for example, super busy, and he has to do his tasks simultaneously. But what he actually does is he reaches a stopping point on one thing that he's doing, and he switches gears and works on something else. So concurrency is how you maximize CPU work, about how you distribute that work across the chip. And most important, concurrency is all about understanding what you're waiting for and capitalizing on that time. And concurrency is often confused with parallelism, so let's get that out of the way first. I can't find a better graphic that explains this more simply, but concurrency, again, is about handling more than one thing at a time. And so basically it's task management. Parallelism is about the actual act of doing more than one thing, or breaking up the same thing into multiple things and running them all at the same time, usually initiating them all simultaneously at once. So unlike parallelism, in concurrency, you're focused on timelines and how you go about spreading work around across the CPU chip. One test I like to use on developers is if you can lock up an application that does parallel work simply because you have to sit around and wait for a parallel job to finish, you're not being concurrent. That's not really what concurrency is. Now, when you're running a parallel task and you have managed to distribute or segregate user interaction from which jobs are running at which times, and then also segregating, collecting the results, and then delivering that either timely to the user or asynchronously, and you're able to do that with no breakage and or no stopping the user if the user's not stopped at any point. And at that point, you've basically built concurrency. So for any of you who used SAP, you'll know this well, and I didn't pick SAP for any particular reason, but oftentimes you'll run around or run into some long operation, and your client will lock up waiting for the server to return. A lot of apps still continue to do that. So the classic single-threaded wait state we all know and love. I input something, and I'm waiting for that to finish and for it to come back. If it's too long, it can trigger support calls. It reduces the prestige of your own software. And administrators who poke around on the server side, they see a bunch of cores doing nothing for the most part. And you've probably seen that a bunch of times trying to debug slow response issues. Well, for .NET, we have the async await pattern. Now, I'll tell you what most .NET programmers do when they go and take an existing project and they try to make it a little bit more concurrent, more asynchronous. What they're really doing is they go and detach the GUI from the long-running operation. So how they fix that is you give the user a little feedback to let them know what's essentially, it's now a batch job that's running in the background. We give them some kind of dialogue, or it could be a job list, it could be an animation, it could be just something at the bottom of the screen, something to let the user know that we're taking care of what they asked for. Now, we've done some concurrency here by breaking off from the main GUI thread to launch this dialogue right here in the middle onto another thread, and then we launch that long-running operation. I want to say for most concurrent apps that I've seen coming out of partners, this is about the extent of what they're doing. They're not really attacking that long-running operation. Now, going further, of course, if you want to give feedback, you're going to have to actually flow back out of that long-running operation and send progress reports back up. So then you're going to have to interrupt the GUI at some point. So there actually is a function. For WinForms, it would be called begin invoke. I think it's also the same in Xamarin and some other GUI toolkits. And then that's where you can go and give updates to the user. But we're still not tackling this thing at the bottom. And it's freaking complicated already. Just making this asynchronous just to the user, basically faking concurrency to them, which is terrible. So I'm not going to go deep in async await in C. We're going to go into something else. I'll get to that. But let's talk about that long-running operation, how we might want to approach that. So I'll show you what a typical C# developer would do. The first thing that they'll look at is they'll look at the long-running operation one here. So let's say I'm taking two pieces of data, they're very large, and then I'm doing some calculation or some combination of a result, and I'm returning that back to the user. So I might break that. Let's focus on the first one. Okay, I'll launch two threads, split the work in half, and then, I'm doing it twice as fast. Okay, we still have to collect the results. You still have to pass it over to the other half that is handling, the data after you've done whatever it is at the first part of your operation. Doesn't matter what it is. Okay, congrats, you just did parallelism. It's still not. This is still not concurrency. You are getting a little bit more efficient though, and this is a cheap win. Let's say I start doing part of the second operation when I have a small part of the first operation finished. So let's say I have 10,000 items or 10,000 assets, and I'm going to go and take 100 of them in a batch, and then I am going to launch a part of a long-running operation. That's what that LO2 is at the top. I'll do the second half of my work, spin up a thread, and then go do that separately. And then I'll just, down at the bottom, I'll just run through all 10,000, and then I'll just kick off a thread each time that I've got a batch, okay? I'm getting a little bit closer to concurrency. And actually this is technically being concurrent, because those long-running operations up at the top could take n number of seconds or n number of milliseconds. You really don't know how long it will take. But if we throw parallelism back in, now it gets more interesting. So I'll launch multiple workers that start on operation 1, and then they in turn fire off workers to hand off what they did over to operation 2 for those small pieces of work. Then I'm going to have a separate thread running on a different core that is just going to sit there and receive results like it's a big giant wicker basket. And then I know when I start the job about how many results I'm going to have. I'll spin up a whole bunch of threads. They're going to independently launch threads of threads. And then this is basically just going to create a storm of work all across the chip until I have all of it collected, and then I finally return the value. This is really what concurrency is. Doing this in a lot of toolkits is not easy. So when you're arguing with your dev staff over performance, your devs will argue amongst each other on how best to address problems like this. But what sucks is that concurrency in nearly every software tool chain is considered, like I said before, it's some sort of advanced feature. So it's likely your staff might be experienced to some degree, but they're really not that proficient at it. To make matters worse, most of the SDKs that you've got require you to understand the basics of what the abstractions are and the SDK around the chip itself. So you have to get very technically detailed oriented to understand exactly what's going on under the hood, because if you don't, you will produce code with race conditions where threads can't agree on which one should run, deadlocks where threads can't agree on sharing a resource, memory leaks, and did I mention this stuff is also a nightmare to debug? Let's talk about Golang. So there is a Google conference going on, by the way, a couple blocks away from us. So this is a new language toolchain that Google developed back in 2009 because they, like everybody else, spotted this problem, and it was hurting them. So they came up with a completely new toolchain that is used everywhere at Google. And concurrent programming is much, much easier with this. So we scrapped the whole idea of threads in Go. We use this new concept that's called a goroutine. These are discrete units of work that we say run independently of other work. Now, Go under the hood does use threads, but you don't care which thread is servicing your goroutine, or you don't care how many threads get instantiated. Go does all of that for you. So you can think of a reason why Google might have wanted to create something like Golang. When this photo was leaked of a column of racks inside of one of Google's data centers, it was wonderment to just about everywhere, to everybody. Those server motherboards there just sit naked, no metal casings. And they're just sitting there on just open trays. They're just like little dinette trays that is just thrown in there, and it's basically just one big gigantic toaster oven. And the reason why is all the CPU chips that are sitting on all of those motherboards are all being maxed out. All the cores that are on every single proc, on every single board, going from the bottom to the top of that rack in every column is being maxed the hell out. So you can imagine, the heat, but can you imagine also the amount of work that they're able to accomplish? And that's all the code that's running on this is all concurrent. So they're getting a great amount of throughput. Let's talk about the language itself. Go mimics C. So if you're familiar with any of the Algol family of programming languages like Java, C, C#, any of those, Golang is going to be very familiar to you. And I forgot to mention one of the principal architects that created this language is Ken Thompson. If that name sounds familiar, that's the Ken Thompson of AT&T Bell Laboratories, and he now works for Google. He wrote the first edition of Unix and is also one of the creators of the C language. That's him there on the left. He doesn't look like that now. He looks more like Pat. So Golang is not difficult to use, unlike C. It's got strong typing, memory protection, the memory's managed for you, so there actually is a garbage collector, unlike C. The data types are modern, so like C doesn't have a Boolean type. They kind of fake it. There was a hack to put one on there. Same thing for strings. In C, you have a pointer to a character array. That's how strings are done in C. So you don't have to deal with that in this language either. The cost of launching asynchronous operations is extremely small. Very, very small. And that's unlike Java and C# or .NET. Instantiating a thread, you have to do some preparatory work in the .NET stack and also in Java. And you're going to see how ridiculously easy it is to do in Go. And then if you also performance test it yourself, you're going to see that it's just lightning quick. And it's very cheap. And unlike just about everything, reading any concurrent code in any other programming language, it can become a nightmare just to be able to read it and Go. I promise you it is very readable, and we're going to see how that works. So before we actually go into the language, I want to show you some elementary mechanisms of a concurrent app and then a spicier pattern of concurrency, so we get a concept of what a concurrent app is really doing inside the computer, what's actually happening. So let's start with a pattern all of us know. The timer pattern. This pattern is so old that even VB people know what this is. So I need a job to run in the background somehow, stick a timer control on it, write some code, that tick event, and then I can configure how and when the timer event triggers or re-triggers or only runs once. And this is basic scheduling of a background task. And the code sample on the right, that's not pseudocode, that's Go code. Next up is the Fanon pattern. In the Fanon, what we're doing there is we're running multiple jobs and we're telling them to send their data over to another job that's running. And in this situation, we have two producer jobs that are launched from the main thread, and when they have data to send back, they're sending that back to main, and then it's farmed out from main back over to a third worker, which we just called the reader here. And this type of pattern is fairly common if you want to think about logging. This is a common way to do concurrent logging where you might have, like say, a bunch of threads running at once doing certain things, but you still need them to log somehow. So to be able to do that concurrently, you have a separate thread that will sit around, and then it will just wait for inputs coming in from all of your other threads. And then you just turn around. The reader just does nothing but just writes it to a file. And it does that synchronously. So there's the code that implements that pattern over on the right. Still very readable. It's not pages. It's just about 20 lines total, minus all the syntax. The last pattern is called the worker pattern, or the fan-out pattern. And this is how your corporate web server actually behaves when it's running. So from the main timeline, we can see that there's a series of 5 workers that are launched, each with their own separate timeline. And each worker in turn has 3 extra sub-workers. And it's the sub-workers who are taking care of individual tasks while the 5 workers fanning out from main are handling coordination. So you can think of the 5 workers as a thread pool, if you're familiar with thread pools in .NET. And, but this doesn't actually map one-to-one to threads. Go actually optimizes where things go on a thread on your processor. In this pattern, we can easily scale up the number of workers and the number of sub-workers that each worker has in Go. And Go will ramp that up to basically exploit whatever architecture that you've got. So if you've got a Ryzen Threadripper or you've got a little tiny baby Raspberry Pi sitting over to the side, you can run it on both your data center and on the edge. And with the same code, you just tweak how you want to, how many concurrent workers that you want to spin up, or you could just leave it to Go to figure that out for you. I'll tell you now. I'm not going to go into the code on the right, but that is implementing that pattern that you see there. Doing this in Java would take you pages and pages and pages of code just to get this working right. And you think that's going to be easily understandable to a junior programmer? I mean, not really. So I'm going to teach you guys a programming language, hopefully in 20 minutes. All right, we'll get started. To get Go, all you have to do is go to golang.org, and you just click on Download Go. The compiler for your platform, whatever you download, will build binaries for whatever your target architecture is. So if you're doing a Raspberry Pi, you can do it on Intel, and then produce ARM binaries if you want. You can also experiment writing Go programs immediately. That's what that yellow box is. It's called the Go Playground. So you can just fire that up on your laptop right now, and you can begin writing Go code right there. It'll run it on a VPS somewhere that Google owns, and we'll send the results back to you, which is really cool. It can get you started without having to figure out environment variables and all of that mess. So once you have Go installed, there's something called the Go Workspace. So you create a Go folder in your user directory. On Windows, you create a path off the C drive called C:\Go. And you can check that Go's there by just typing Go. This is your workspace where your code lives. So you can see where your workspace is set to by typing go env go path, or where Go is installed by typing go env go root. And that's just me there, just checking my paths just to make sure I'm sane and I can compile things. And I'm making an SRC folder. It already exists. That's where I'm going to put my code. So let's do hello world. First, I'm going to create a Go package called example underneath the source folder. Under that, you create a file called main.go, and you can rename it to whatever you want, really, but if you want to execute it directly, inside the package file, it should just be called main. From there, I'll write a print line command to print hello world out to the console. Then I just compile it by running go build, and go build executes the compiler, produces my output that I can execute. I can also type go run main.go if I want to, and it does the same thing. So in green right there, that's the binary. This does work like a couple of, if you've ever used Delphi, and there's a couple of other languages, they'll compile all the supporting libraries all into the binary for you. And that's why hello world is that big, because all the supporting stuff is inside there. So let's go ahead and look at hello world a little bit more carefully. All Go files have a package declaration at the top. If it's called main, then this is the entry point to a program that can be executed. So if it's something other than main, then it's basically library code, which can be called by other code. There's an import section where I can reference other code. So right up there where it says import, I'm importing the format library, and that's how you format strings. And then finally, we have the entry point down there, function main. So it's the same as it would be in just about any other language. It's func, and then the name of it's a function. I was about to say method. One thing that's important, though, is formatting of your text. Curly braces are important. Golang, unfortunately, insists that you use KNR style bracing, which means that curly brace must be at the end of that line, not on its own new line. So if you're an individual who likes to put your opening curly braces on their own line, sorry. It will actually throw a compiler error at you. But similar to Visual Basic, instead of using a line terminator like a semicolon like you would do in C# or in Java, you don't have to do that. Just pressing enter the compiler when it is actually doing the lexicography scan, it interprets line endings as statement terminators. So if you want to wrap a statement, you're going to actually have to find a position where you're doing the dot, or you're opening a curly brace, or you're doing an operator like plus or and or, and you can break a line right there. But you can't just break it anywhere that you want and then put in a character that's saying, please continue the line. Variables in Go can be declared with the var keyword, followed by the symbol name, and then the type to be used. If I don't provide an initial value, the 0 value for the type will be used. Every type in Go has a 0 state. So for the numbers, the 0 value is, of course, 0. And for strings, the value is just an empty string. I can also initialize variables when they're declared by using an equal sign. So I'll pre-initialize x to 3. And I'll init y with the value of 5, and then init another integer called z and give it the value of x times y. Change the print statement to print out z, and I should get 15. Going deeper, I can drop the var declaration syntax altogether, because if you noticed with the variable z, Go is capable of inferring what that is. So I'll drop the var and just add a colon with the equal sign to make this a declarator. Then you just drop the type statements. Go knows that these are all ints, and I'll still get 15 as my output. And it's basically the same program. So it's a nice little shorthand. You can actually make a little bit more readable code for you. If statements in Go are simple, note that there are no parentheses placed around the evaluation condition, though. So if you've been programming in C or C# or Java for a long time, normally you would open a parens around that, that x greater than 6 right there. You don't do that in Go. There. Yeah, the compiler will complain to you. Now, if you're doing groupings, so you have like x times y, and you need to check that if that is greater than a times b, then you can put parentheses, but not around the entire statement. There's also else if and else. It's a very simple logic flow. Again, most of you are familiar with that. Now let's look at arrays. Arrays are of fixed size and are declared with a certain type. So here I'm declaring an array that holds 5 ints. The ints will be initialized with the 0 values, so when I print the output of this, it'll be an array of 5 zeros. I can index an element in an array. So array index start at 0. When I'm editing index 2 of the array, to put in a 7, that means the third item in that array is going to become a 7. So it goes 0, 1, 2 right there. That's now a 7. I can also pre-initialize an array with values by simply slapping curly braces on the end of the declaration and then just provide the values there. So I have an array of 5 ints. I'm putting in 5, 4, 3, 2, 1. There we go. Go has this neat concept called slices, which are actually views onto an array. And it allows you to add and remove things to it, because arrays, fixed arrays, are really, they're not very useful, are they? So to declare a slice, you just take the array size out of the square brackets and leave it empty when you declare the type. And when you declare a slice, if there's no underlying array, you don't have to create it. Go creates one for you under the hood. Slices, the reason why we have them is it allows you to be more nimble with arrays. So here I can slap an element into an array with a built-in function in Go that's called append. This returns a new array back into A, but under the hood, the memory allocation and data shifting is optimized by Go. So I can write this the lazy way, because the lazy way is more readable than handling pointers or using wrapper objects or container objects like in Java and C#. I can just do it this way. So you think that might not be performant, but actually it is. I actually created this use case in Go. Go also has a data type called maps. Maps are basically dictionaries or associative arrays. So to declare a map, you use the keyword map followed by the type of the keys in brackets. And then after that, followed by the data type of the items that you want to put into the map. So I'm going to make a map with the keys being strings, and then it's going to hold a value that's an integer here. Now, Go has a function called make, which finds memory to place the map, and we can assign that to a variable and then populate the map with data. So here I've created vertices, and I know this is wrong because I looked at it and balked at it in my hotel room last night, but just bear with me. The square has 3 vertices. I think I got that one wrong too. A dodecadon 12. But what really matters here is what does that look like when I print this out? And that's a map. We can refer an item in the dictionary by using its key. So if I want to pull out what the value of triangle happens to be, I can just do that. And then we can also remove things out of the maps from slices by using the delete function. So there I just poofed that square. Loops in Go are very easy. There's only one keyword for all types of loops. It's for. Everything is a for loop in Go. In a for loop, we initialize our counter, then we put in the stopping condition, and that's how we increment. So I print the counter 5 times. So I just set my counter. I want to stop at 5. I'm going to increment by 1 each time. 1, 2, 3, 4, 5. Or 0, 0, 1, 2, 3, 4. To turn a for loop into a while loop, I just remove the counter and leave the stopping condition. And that will change it to a while loop. This does the same thing as before. Don't ask me why the architects decided to implement looping in this way, but if you think about it, it does work. Now, the for loop syntax is actually pretty powerful. So to iterate over an array or a slice, there's also a keyword called range. A range pings out both the index and the value at once, which I can then loop over to work with the contents of the array. There's also an overload in the print function that will take all the arguments you send to it and it inserts spaces for you so you get a little neat table. That's super convenient. Not to be outdone, you could do this over maps as well. Here I had declared, I'm going to declare a map of tanks, and I've introduced a new data type called float64, double precision for storing the tank's utilized capacity. Instead of an index value pairs, we're actually dealing with key value pairs, so I'm just going to adjust the wording of these variables so that I'm correct. So you no longer have to do nested loops to go through dictionaries in Go. Which is great. All right, this is the last data structure I'm going to show you, and then we're going to move on to control flow. So let's go into structs. A struct is the same as it is in C and C#. You use them for associated data. So you tell Go you're defining a type and you give it a name, then you put in the fields with their types. So I'm defining what a tank is, and the tank's going to have a name and it's going to have a capacity. So to create a tank, you just make a tank variable, and just like arrays, you can initialize it in curly braces right off the bat and stick in all the values if you want. And when you evaluate or you print out what that struct is, that struct variable, my tank right there, you'll see you have a struct. And it will print out on the console in curly braces. Pretty simple. All right, we're almost done. Yep, we're almost done with that. All right, let's do control flow. All right, we've been lounging around the main function for long enough. Let's see what leaving a function looks like. Declaring a function, you use the func keyword, followed by the parameters coming into the function. And what's unusual, we'll see later, is that you can actually have multiple outputs coming out of a function. Then you do your computation, you return it. And I'm going to doing a sum here just to show you what that formatting looks like. And we should get 5. Woohoo! Okay, functions are great. We all know that. Let me show you something common in Go syntax. So instead of doing a sum here, I'm going to change this to a square root function. Now, since negative square roots return complex numbers, I'd like to return an error when that happens, because I don't have time for imaginary numbers right now. So I'll define a square root function that takes an x input, but it will return an output, and the result can be also an error. And what's cool is that I can have more than one output from a function at once. So I'm going to evaluate when you send me a number I don't like, and if I have a number that you sent me I don't care for, I'll also fill out that error there and return an error back to you. But I can also return a good value, all in one call. So for the square root, I'm just going to bring in a math package. I'm also going to bring in an error package so I can create an error structure. And so when you're adding extra packages, by the way, they go in parenthesis up there at the top in the import statement. So since I don't have math, I'm going to add math here. And inside math, you get your normal math functions. So your square root, your sine, your cosine. Now, back up at the top where I call the function, I can get one variable, but the function actually returns two variables. So let's see what happens here if I just do result equals square root of 6. This is going to blow up on me. So it's telling me one variable, but the square root actually returns two values. So I need to handle that. I could put it in a variable, or instead of ERR, if I don't care for it, I can just put an underscore there and just throw that away or ignore it. In this case, I do want to test, and I want to see if I get an error back. So if error is not equal to nil, that means there's an error, and I'm going to print out what the error is. And Go is fully Unicode compliant. So yes, I can put emoji in the console, which is super great. So if we can get the Unicode people to add in all of our Pi symbols in there, that'll be awesome. Like, my tank has a sad, and then just change tank to a tank, and then frowny face. All right, now here I've changed this a bit to show you what I showed you the sunny side case, but here's the frowny faced case where I do pass in a negative square root, and then you can see there at the bottom, error prints out nicely. All right, one more concept. Forget it. All right, pointers are used in Go. So if you're from a managed environment, I'm going to tell you right now, I started in .NET in 2002, 2003. And we were told right away, just like we were in Java, that pointers are scary and they're the devil. And don't go near them. And that's because pointers in most languages are untyped. They're basically just 32-bit or 64-bit numbers, memory addresses to the cells on your RAM chip. So because they're not typed, you can do lots of damage with pointers. But in Go, you're actually conditioned to use pointers. But pointers in Go are typed, and the compiler actually strongly enforces it. So pointers are actually great, and I use them quite a bit. So another thing that was in Go, I mentioned it earlier, there also is a garbage collector. So memory, you don't have to write a malloc, you don't have to worry about individual, you don't have to handle memory allocation directly yourself, but you still get to use pointers. And you can still easily do asynchronous programming, all in one spot. And it really is not that difficult. Now I showed you the language syntax. Now you're a Go programmer. Okay, I didn't actually show you any concurrency yet. So let's go into that. Now the syntax of the language, it was easy for me to talk about. Let's do concurrency, how that works inside Go. All right, done. You just throw the word Go in front of a function, and that launches that in its own worker. That's what a Go routine is. That's it. Now if I actually run this, well, let's go ahead. I'll show you what it looks like if I run that example. Right there at the bottom, when I run it, I don't get my output. All right, welcome to the world of concurrent programming. You're going to have to care, you still have to care about things like timelines. So this is the simplest you can get in a concurrent program in Go. This is basically the hello world. But if you do it like I did, you're going to be wondering here what's going on. So let me show you how this works in a timeline. Whoops. I launched my function in main. It creates a Go routine, so it took my do something function, and we branched off main to go do it, and it left the main thread. But Go routines are asynchronous. So if I'm not waiting for do something to come back when the main loop is running, the main loop is just going to keep on trucking until it has nothing left to do anymore, and then your program ends. So the program quit out because main had nothing left to do anymore. So bye. That's why you don't get any output. So main clocked out early. The do something was still in the preparation stage of sending results out to the console, but the program quit out. And that's why it looks like that. So one thing you can do is you can hold main open. So to get the concurrent worker to print out its stuff, I just have to find some way to hold main open. Now, there's a billion ways to do that. I have one that's called the Cindy Lauper method. So time after time for duration max N64, which is a huge number, I'm going to sit around and wait for an output out of a channel that will never arrive. And channels are that left pointing arrow syntax you see there. And when I run this now, the main loop will run forever. That gives my goroutine enough time to send its output. By the way, holding main open is actually how you write a system daemon in Go. And a system daemon for you Windows people, you call that a Windows service. So if I run this now I can see what the goroutine did. All right, now I mentioned channels. When you send workers off to go do things, you expect them to return results somehow. And as they work, you're going to want intermediate results or you're going to want the final results. Channels is how you go about doing that. Now, this is going to get extremely complex, so get ready. That's it. A channel is just a pipe. All that happens with channels is you take data you're holding and you send it off to a channel. How it gets there, you don't care. I don't care. You don't have to know everything that Go is doing underneath it. All you have to know is that there's some receiver at the other end that's going to pick data up off the channel, and someone has to put it on. Except this is way more efficient and easier to do than setting up email on your smartphone. Now, I've seen a lot of people botch introductory examples on channels, so I wrote my own. I'm going to do this in just one shot. I'm going to start off by creating that do something function again to print out a line, but this time I'm going to add a channel for it. Now there's a type called chan, and just like when you create a map, you use the make function to make a channel that allocates the memory space for it. I'm going to create a variable called messages, and it is basically going to be used to pass messages back and forth from the channel. It's up to you where a channel is actually going to exist. But in my example, I'm going to just create the channel in main. So my goroutine worker can see the channel, and I'll stick it on as a parameter over and do something by using that arrow notation there. And then when I want to transmit, I just go ahead and just take the value, and I'm just going to left arrow it into the chan. And then up at the top, I launch my function. I'm going to pass that channel over to the function. And then when I want to receive out of the channel, I can put that in another variable. And then so if I have the left arrow pointing back in a declarator statement there, or an assignment statement there, then I'm pulling something out of the channel. So if I write it this way, not only does the program terminate nicely, but it allowed the goroutine to finish. So the program execution will actually stop right there at that highlighted line. At format.print line, if I'm waiting for something to come out of a channel but it's not there, then it's basically just going to pend until something does arrive. So how do you know what you're working on? How much of it's done? Who's doing what? How do I make sure that I don't try to process something when I'm not ready to? When you're using channels inside of a goroutine and you put things on a channel, you receive things off of a channel, the execution of your goroutine stops in the goroutine and also from whoever's listening on the other side. And you can have goroutines talking on the same channel, and that's what most people do. So if you're familiar with concurrency in C++, when you're using things like critical sections, mutexes, semaphores, all these other constructs to synchronize. So I know I have to be at this step over on this thread and at this step over on this thread to be able to trade data safely and not have one thread overwrite the memory space on another. You don't have to worry about that in this because all of that work is taken care of with the concept of channels. And we like to think of programs as basically like a recipe. You have a specific order of tasks, things that you're going to do step by step by step. And when you're running two separate jobs, the syncing of those two jobs happens when you're receiving data across a channel. So on the right, I have a goroutine running to process some intermediary results. And when it's ready, I send it out on the channel. Now, if there's nobody ready to take it off the channel, my goroutine over on the right is going to hang there until someone does come and collect it. On the receiving side on the left, I'm receiving it there at step 6. So I'm always guaranteed when these two goroutines are exchanging a message, the goroutine on the right is going to be at step 26, and the one on the left is at step 6. That's always guaranteed. And channels, by the way, are two-way. You can, if you don't want to communicate bidirectional on a channel, you can create two channels. So you can have one where your sub-workers are actually going in one direction, and then your commanding main thread or wherever it is that you're launching can push out. You can also have channels inside of channels, which is crazy. Another fun thing that you can do with channels is specify a channel size. So when you create a channel, it always has a size of 1. That means the channel can only hold one thing in it, so your calling routine will block and your go routine is going to block until the item transits across the channel. But if I give it a size, I don't have to block when I put things on a channel. So if I set the size at 3 here, that means I can put 3 things on that channel before my go routine or wherever I'm pushing stuff onto the channel will start to block. So if I loop trying to put on 10,000 items onto the channel, it will loop 3 times, and then it's going to hold, it's going to stick, until someone picks up an item. This is how you do queuing, asynchronously in Go. Each Go routine will block, waiting for an item to come off the channel. You can hand over items to any Go routine you want, or you can spin up the same function as Go routines. So if I did something like this, where I just do something 3 times, I now have 3 workers. I passed it the same channel. And if I create a loop and I send, let's say, 10,000 items onto the channel, then Go is going to select each Go routine and give it 1 item off of the channel and feed it directly into that Go routine. And that's how you do that fan out pattern, by the way, the worker pattern. Now you're a Go programmer. Literally, this is all you have to know in order to, I mean, I can print out a certificate right now if I had a printer. So, now that we've started on our way to doing concurrent programming, let's do a project. We're going to do a massively scaling web application server that's going to have 50,000 users. Let's say it's an OMS display or something like that. Now, I know what you're thinking. Okay, done. 2 lines. Well, that's your application server, but this is a common pattern for Go programmers. The request-response mechanics of a multi-threaded web server, the pipelining, pooling of connections, the handling of memory space, all of that business has already been done 1,000 times before. So getting a REST service up and go really just involves bringing in the web server package to route URLs, and there's an awesome code library on GitHub that you can just bring in by adding it up there at the top. But, okay, that's neat, but this web server doesn't do anything. I need it to return data. Okay, this is what a REST API pattern looks like in Go. So you define what the URL patterns are going to look like, the HTTP verbs that your web clients will call. Then you just write a func, which will become a Go routine that's launched for every inbound request that comes in on those paths. Then you just add more sugar for authentication and identification as you like. And your business functions are already in a Go routine. You can spawn more Go routines inside them if you need to return the data as soon as possible while you're still doing extra processing back somewhere else. Or kicking off that long-running operation and just passing a token to the user saying, yeah, I got your job. I'm working on it. And then go contact this other URL to go find out what the status of your job is. So how do I pull my Pi data into my Go programs? There's one of 2 ways. The direct way is to send requests to your Pi Web API server. Now, while OSI doesn't make a Golang client as a product for Go, you can easily make one yourself. If you go into your own Web API machine, under Help, there's a section called the OpenID2 specification. The full details of all the inputs and outputs on all the controllers in Web API are inside there. It's downloadable into a special format. And you see that word, the hyperlink that says Pi Web API Core Services here, that word here. When you click here, that actually downloads the Swagger spec. And that's me showing the Swagger spec right there. You just download that into a file, and then there's a tool, open source tool that you can run, and it will generate a proxy client for you so that you can actually hit your Web API server inside Golang. So that's the tool, swagger.io. Oh, by the way, my colleague Tiag, right after lunch, is doing a Swagger talk. I think it's either in this room or the next one. So if you want to learn more about Swagger, and especially pepper my colleague about, I want a Golang client for Web API, that's the time to do it at I think it's 2:30 or 2:35. Literally, all you have to do is just throw the spec file into the tool, and then you'll get back the source code out in Go, all in a zip file, and then it's compilable, and then voila, you have a client. Now, it doesn't include Web ID manipulation. If you want Web ID manipulation, come see me. You can just email me directly, or you can contact the technology enablement team. I have a Go file that will translate Web IDs for you. So if you have a path to your AF element name or your attribute, and you want to turn that into a Web ID, or you want to do it the other way around, extract what's inside the Web ID, back out into, get the point IDs or the paths off of it, I do have a Go file for you, and I am going to put it up on PySquare. So you can go to PySquare tomorrow morning and actually download that piece of code. And one quick win you can get out of Golang is doing a mashup of your own corporate data out of your own libraries you've already built with PyServer data. So this has been asked for by a ton of customers, but we've had no real way to go about doing this easily. Now, I had Chris Nelson, the head of software engineering at OSI. He came to me once wanting to do a research project so that Pi customers could build their own .NET plugins and actually insert them into the Web API server. Because it's already highly proprietary, that would also require writing a special interface and then teaching customers that interface. And frankly, it's just easier to use a technique that's called reverse proxying, where I have my own users going to a proxy application server, and from there I distribute the calls to the two platforms, like my internal platform and my Pi system, and then that's where I can mash the data together and then provide a unified output. And then I can also handle the security and authentication the same way by doing it there. Besides doing Go in the data center, the edge is also a great place for it. That's where a lot of development and or concurrent development is happening right now, is actually on the edge. So I have some templated projects where most people are doing this already. So I have one that's called Project Cheap, Concurrent High Efficiency Edge Platform. Basically, instead of creating a board for one sensor, I build a bigger board, a concentrator, and I'm going to have a ton of sensors hooked up to that board, and I'll just handle all that streaming data concurrently all at once, batch it all up all at once, buffer it all at once, and then compress it, and then send it up back to the data center. Another one, moving your calculations that you do, your analytics, off to the edge. One quick win is if you are the type that has to do moving averages of your data. So if you have, let's say, 7-day, 30-day, 90-day moving averages, so those are real-time analytics, you could actually save a little bit of time just doing that right there on the edge device if you're basically building your own sensors. Another project I call MegaBuff, and that's basically expanding sensor resiliency, ensuring no data gets lost or discarded, and also doing proactive notifications by putting alarms directly on the sensor devices so that field workers that are closest to the devices can see whether or not they're sick or give out audible alarms because there is no uplink at that point. So we need to get those sensors back on quickly. That is another place where you probably would want to do things concurrently. Now, I talked about Web API. Now, there is another secret way in Go to get at PyData, and that is using Microsoft SQL Server as a conduit. So if you are already doing a remote data connection between the Pi system and a SQL box, you can just go grab the SQL Server database driver for Go. It's actually written natively for Go. It's right on the GitHub that you can go grab. And there's actually a native SQL client now for just about every other language you can think of, like for Rust, for Ruby. And you can actually use that as basically as an adapter if you just need read-only access to go get data, or you've already done your mashups on the SQL side and you did it in PySQL, then you can just go grab those views and then they're just select statements to you. That's a faster way to go grab stuff. Now, I am doing a talk with Bodo Backman tomorrow. It's called Modernizing PySQL for the Future. And towards the end of that talk, I'll actually show you setting up a link server between the Pi system and Microsoft SQL Server, if you want to look at that. So I'm going to leave you with this. This is a very experienced programmer on a blog. I am leaving his name off of here just so that he doesn't get attacked by any people who are Java zealots. But he's worked for Java, or he's worked with Java for a really long time, and just about everybody else that does concurrent programming will tell you the same thing. There is really no other toolchain out there that makes concurrent programming easier than Go does. And also, it's as far as getting the projects done quicker, Go is actually a really useful, beneficial way to go about it. And so that's the end of that. I'm going to go ahead and open this up for questions. Anyone have any questions for me? Going once? Going twice? All right. Thank you so much, everybody, for coming to this talk.